move this away. Minimize this. And make this view full screen. Got it. All right. Ready? All right, good. Yeah, sorry for the little delay. I think that we probably had a little bit longer morning session, and the lunch turns out to be a little bit too short. So anyway, we get this started. We're about 10 minutes, so that's actually perfect for Berkeley time. Berkeley time always starts from 10 minutes after the clock. So, I mean, I'm Ima, and also that this afternoon we will actually have a 2 tutorials for this associated with this conference. The first tutorial, this tutorial is about understanding deep networks, right? In the context of learning. This actually consists of, I think, the 4 lectures. I'm the first one, right? The first 2 are related to, more closely related about how do we understand deep networks from more principled perspective. And then the next 4, the 2 other talks is more about understanding the behaviors of deep networks, right? How would you use it? What do we expect? How to explain the behaviors? For example, when you train classifiers, how do you understand them better? The properties, right? So, so the first lecture is about how do I say, the title is ReduNet, right? The white box deep networks from the principle of maximizing rate reduction. You can think about the first lecture is more about the principles, concept, right? You have seen many instances of deep networks, right? From AlexNet to LoLet, AlexNet, GoogleNet, VGG, later on ResNet, and also the so on, right? Transformers and so on. What is going on, right? There are instances, right? Is there anything? How do we understand what they're doing? What's the purpose, right? What is in common in all of them? They come in waves, come in fashion, right? Year after year, right? Can we have some kind of more unified fundamental understanding, right? Maybe they're just the means to the end to serve some common purpose. What could be? Right? The practice of deep learning in the past 10 years, we call it a revolution, but it's largely sort of the empirical approach or inductive approach, right? 归纳法 Chinese calls, right? We try and error. It's almost like experimental physics, right? We discover one particle after another. We invent one mechanical system after another, right? It has always been like that. Science, engineering has always been that. Started with something empirical, something, many instances. It looks very diverse. All kinds of, rigid body motion, all kinds of things, planets, cars, objects, right? Stones, they're all following, they all look different. They behave differently. But at some point of time, people start realizing all these objects, actually all the physical system, obey very simple rules, right? They're just instances. What we saw just instantiations of those things. The question is, could that be the same as well for deep networks? Right? What we see is just the instantiation of something in common, right? After long practice of inductive method, maybe, in science we have two legs of methodologies. One is called the inductive, another one is called deductive, 对吧？归纳法和演绎法, right? So always deductive is sort of, at least, perceptually, right? In the civilization of mankind, deductive always symbolize our understanding about something reach a higher level, right? Slightly higher level. We'll be able to abstract something in common from all this mass majority of instantiations. We don't memorize things one at a time. We start to know there's a common principle behind it. So this is the questions. This is sort of a quest we have been trying to do in the past few years, right? Went back to Berkeley, and we have seen we were really in the middle of that. See all these instances, all this practice, all these applications, right? This explosion of networks and their applications, right? Can we make some sense of it? So this is sort of summarizing with, this lecture will summarize some of that discovery. And even our approach to see how we actually end up with some better, hopefully a better understanding of this, right? So just like everybody else, when we saw, deep networks start getting better and better, we were curious, like, what really make them work? Right? There's a lot of, especially for theoreticians, we try to understand what's going on, right? What is important? What's in common? Right? In early days of theory, we look at one thing at a time. Oh, dropouts somehow make training better. Can we explain it? Oh, layer normalization each layer. That's a big deal. If you don't do it, you lose 10 points, right? Oh, residual link, right? Why? How? Then you write a lot of papers about it. Right, and also that's why deep networks bigger is better, or why it doesn't overfit. Right, contrary to the traditional classical understanding about the larger models, if you have bigger, more parameters, you have a tendency to overfit your data. Right, it doesn't generalize well. Well, it turns out deep network generalizes reasonably okay. Right, it's not that bad. Why? There's a double descent phenomena. Then there's another 1,000 papers to explain that. Right? So all these things is that you're looking at one thing that practitioner found useful. You try to, then everybody tells you, oh, that's it. That's everything. That's what makes deep network work, right? Let's just write a paper. Once you understand that, you understand everything, right? Happened so many times, right? And at some point, I got tired of ourselves, right? So Jesus, this is endless, right? We just sort of dragged by it's almost like, in experimental physics, right? Remember there was a time, that if you have they build all the big colliders, right? Every month, every year, there's a report, there's a new particle get discovered, right? Then sometimes in early days, you want a Nobel Prize, right? Only after a while, they realize they get discovered a new particle every year or even every month. They stop giving you Nobel Prize to new particles, right? And suddenly there's a standard model. Not only explain what are those particles doing, but also can predict the new ones. It fundamentally changed, right? So the things that, so we sort of learned that a lesson a little bit from. Then after a while, my group at Berkeley, we got, a little bit frustrated with this effort, trying to explain one thing after another, right? It's just, before we explain deep networks, before we explain deep learning, can we just refigure out, right? Step back to think about what is learning trying to do? Why we learn? What is worthwhile learning? Right? So maybe we start with that. Maybe the rest is just the manifestation. It means to the end. Deep or not deep, right? Serve a purpose, right? So this is a kind of perspective from there. So we'll start with what is the objective of learning? Then once we realize that, we start to go back to trace what the roots of collect to many classical roots to try to understand learning, understanding the structured data, to learn something useful from the data, right? So there's a rich classical roots there, right? Rather than everybody claim everything came up is completely new, actually quite the contrary. A lot of the fundamental ideas has been there. People have done that, right? It's just a matter of collecting them correctly, and you will understand much better, much deeper. Right? And we'll see. Then another thing is that everybody talk about representation learning, right? What is a representation? Have anyone defined? You want? Everybody, whatever they learn with deep network, they call it a representation. They call it a hidden atom, right? Nobody specifies what they want, what is requirements, what's a property, desired properties. Can we be more rigorous doing that? Right? Finally, you realize once you clarify the objective of learning, once you've put a precise definition about what your desire in the learning, or what is objective learning, what is the desired property of the representation, you start to realize maybe all the deep networks you saw so far, they're just different means to the same end. Okay? Different variations to try to achieve the same goal. Hopefully we'll get to that, including residual network, including a mixture of experts, including transformers. I mean, the next lecture, especially Sam will precisely talk about that connection. So this lecture is about the concepts, established concept. So the early days, right? So in the very beginning, when deep network comes out, right? Before deep networks, this century, right? The first 10 years, people work on something called compressive sensing. You probably get it. That's so inspired this conference, right? The parsement, try to seek the sparse representation of data. Try to solve differential equations that find the sparse solution, right? Now, this is a classical algorithm. And towards the end of the next lecture, you'll see how this algorithm plays a crucial role in deep networks, right? This is the classical system to solve linear equations, y equal to ax, to try to find a sparse solution, right? The algorithm looks like this, okay? 2 lines, okay? 5 minutes in MATLAB, you implement it, okay? But look at what it does, right? It's an iteration. You do some linear operation on your data, input, data from the previous layer, then you do some thresholding. Sounds familiar? This is the predate deep networks, okay? Way before, okay? Now, of course, you like to draw diagrams, right? You can see that if you draw a diagram, there's some linear operators plus some thresholding. What does it look like? At the meta level, look like a deep networks, right? Turns out this is exactly what Yang and Kuhn worked on before 2010, okay? Before the deep networks start to become popular, okay? Because he realized this is just look like a neural network, and it can be trained. But by fine-tuning this network, this algorithm, treating those parameters as a fixed trainable, you improve the capability of the algorithm to recover sparse signals. This is also something Professor Gao Zhenhua, we worked at Shanghai Tech, right? This is saw this connection. But this is observation, right? This looks like a deep network, we can train it. And everything's still very inductive, very heuristic, okay? Right? They inspire each other. There's no formal rigorous connection. They just look like each other. They're doing similar things, okay? It's at that level. Nothing really rigorous, right? So now, if you wanted to formalize the sparse recovery, right? This is then you give y and a. You try to solve for x, right? This is a simpler problem. But what is the harder problem? Harder problem is I don't even know the structure of my data, right? I don't even know the code book of my data. I have observation y only. I know for some code book, maybe my data is sparse, has structure, right? So this is a much harder problem. It's called a dictionary learning problem. I have to learn a transformation to sparsify my data, okay? To make my data better, but make my data lower dimensional. But this is a classical dictionary learning problem, okay? You only know y, you try to learn a and x together. It's classical learning. Okay, I will forgo this. So it turns out that algorithm, this is also a problem we worked on in the past, right? We try to discover the most effective algorithm really resemble the same thing, right? So this turns out to used to be believed is a very hard problem, right? In signal processing and so on. Turns out there's a very effective algorithm to solve this, right? Again, iterating some smooth transformation and do some thresholding. And if you convert this algorithm in an equivalent form, right? Take each iteration, right? This algorithm naturally has a deep network flavor interpretation. Each iteration just a simple operator and with some thresholding. Simple operators with some thresholding. And so we'll be able to learn this dictionary, can code your data most effectively, right? So don't feel bad you get lost, right? It's just the motivational connections to different things, right? So basically, deep network is just an interpretation to some sense, right? There's a way to interpret this kind of optimization algorithm, right? You can naturally see many optimization algorithms already resemble the structure of what we saw, the meta structure we saw in modern deep networks. Then turns out all the algorithms, the most effective algorithm people use to solve dictionary learning, power iteration, ICA, independent component analysis, are exactly of the same type, okay? So those are the sort of connection to early sort of heuristic seeing similarity between modern deep networks and some optimization algorithm, right? So next lecture, we're going to strike everything home to see exactly why they come up with, right? How they connect it. right? This is just observation, early observations, right? We saw similarity. Now also, our first understanding, this is what I did at Shanghai Tech with some of the folks there. And so at the time, when deep network first came out, right, everybody say, oh, deeper is better, or bigger is better, right? Or everything back propagation is everything, right? So this is something we tried at Shanghai Tech when our first early attempt to understand deep network. So we try to ask the question: isn't deep necessary? Why deeper? Is back propagation necessary? Why have to back? Right? Nature doesn't do back propagation. Recently, Hinton admitted that. Then how did we did it? How our intelligence system realized? What is the computation mechanism? So this is the sort of early paper we did. It's just, we construct, can we do the exactly opposite? The shallow networks, everything's forward, completely not trained. Can you achieve good performance? This is what we call the PCA net. Right? Every layer is a forward PCA operator. And based on very simple, the nonlinear activation is just binary. Simplest 2 layers, 3 layers. Surprisingly, at least as of 2015, right, at that time, this simplest, arguably simplest, naive network is the state of art on some of the most challenging face recognition systems. For 30 years of study of face recognition, nobody bothered to try the simplest idea. Why? We had a very hard time. By the way, the work we did is around 2013. It took us 2 years to publish a paper. Why? Because it was rejected by every single conferences. Because they didn't believe, right? Such a simple algorithm can achieve state of art on face recognition and against what's popular at the time. Everybody advocating deeper is better, bigger is better. No, the simplest model performed just as well. There's a lot of things we don't understand, right? It happened again and again, guys. What is popular can disguise what some of the gems of the ideas. And we start to see things, right? Nowadays, everybody talk about transformers. Turns out transformer actually does something very, very similar to this, right? You'll see later, right? Those heads are doing exactly some of the dictionary learning. And the PCA type 4 mapping. And also, they actually sparsify the features, right? Even empirically. And later on, next lecture will make this absolutely rigorous, okay? But this auto position, this is, even behaviors like the dictionary learning, like the sparsifying, they're doing this, right? But can we really collect everything? Now, so this is what happened in the last 10 years, right? There's a lot of, a lot of instances, networks, a lot of applications. Also, there's a lot of sporadic theories, try to explain one thing at a time about networks. And also, there's a lot of, sort of vague, what this looks like, that, right? It's like an optimization. This is similar to doing this. But then how do we really pin down everything, right? Have a sort of framework can actually explain, if not all, it's most majority of those problems, pieces. Fit them together in a nice way, right? So that's what we actually set out to do. As I said, before we understand the phenomena associated with deep networks, deep learning and applications, algorithms, so on, right? All these instances. Can we just sit back and what the learning trying to do? What is object? Why do we learn? Why do we need a memory to learn, to memorize something? Why? If the world is random, is there anything worth learning? No, right? If the weather tomorrow is random, why? We don't need a forecast. Right? I just take a big close my eye, take a random guess. It's equally good. Nobody can do better, right? There's no need of memory. There's no need of learning at all. There's no need of science, right? If the world is random. So hence, the fundamental reason we learn is that the world has something worth learning, amenable to learn. Okay? So hence, we observe images. We hear sound, our touches, right? Those are the senses of the world. Why we sense the world? Why there is a need to sense the world? Think about that. Ask yourself some really annoying questions, okay? If the world is random, there's no need of sensing. Act randomly, right? So there are things worth sensing From the sensed data, there's things worth learning. Okay, hence the words are random. So despite the data we receive is massive, right? Millions of pixels per second bumping through our retina, right? But their information actually is very, very, compared to the dimension of the data, the information is highly condensed. There's a structure, there's a predictable structure in them. The structure is actually, intrinsic structure is highly low dimensional. Right? See, some object, doesn't matter it's a bus or a bicycle heading towards you. You know if nothing stops it, it's going to hit you, right? It's going to travel in a straight line, right? That straight line is very simple, very predictable. But those are the structures our science or physics trying to discover, right? The same thing with our intelligence, right? We're building predictive models. We're learning the structure of the data of within our observations, so that we build a model for it that we actually use it to predict. So hence, learning is trying to learn the structure in the data and representing them in a very structured way, easy to remember, easy to use for the future. Right? So once you realize that, in fact, the early success of deep network happens to be a special case of what it's trying to do, right? Especially the early success of deep learning is trying to actually, let's classify different classes, right? We have many, many images, right? Let's say the red dot spans an image of Apple, right? This could be, the dimension could be very high. The capital D could be 1,000,000 pixel if you have 1,000 by 1,000 images, right? Each pixel is a coordinate, meaning that each image is representing a dot in one point in the space of 1,000,000 dimension, right? So different images represent different dots, right? Then the second line could be maybe a bird, maybe a cat, right? So this the image of apples, cats, they concentrate on their low, small regions, right? And hence deep network is saying, well, can we just classify, right? Map all the image of, let's say, image of the apples to a something very simple, singleton, right? 1000, right? Anything different, like cat goes to 0100, right? See, even classification is a typical example to convert something potentially high dimensional, complex, to something very structurally simple and compact, right? If there are structure in the data, allow that, right? Then of course this process could be very, very complicated, right? Hence people are bold enough, like Hinton, we don't know how to do this. Let's just model this mapping of some deep network. So we train end to end with enough input output, right? That you see very good success, right? Especially if you try this kind of cross entropy is try to precisely encouraging that measure of simplicity, right? The output of the network has to match the 100, the label, right? So, and actually give very good classifiers. But it is actually good. I mean, but also remember, you get what you reward, right? If you want to minimize this kind of make your output of your network match with the class labels, you end up with the output feature looks just like the one hot label. This is a phenomenon called the neural crabs. I think the two last lecture will go into deeper about the behavior, why that happens as well. Right. So now there are actually all kinds of elephants in the room, right? Turns out the people said so a large deep network actually can fit any data. You don't know what learned. Turns out you can randomly shuffle the labels. You can label cats as apple, apple as donkey, whatever. You force the network, you redefine the label of every image. Turns out you can always train a network to fit the data input output perfectly. Right? So you question what the heck you're doing. Right? The network can learn anything. Garbage in, garbage out. Right? Similar to the large language models. Right? If you train on bad data, the memory, the network is going to memorize the bad data, bad relationships. Right? And also, especially what's going on, it's a black box. Nobody knows what the network learned, right? What is the early days people do image segmentation, try to visualize even a single node, right? Even that is not obvious. You have to do deconvolution, heuristic, what roughly you get from the receptive field, looks, you stare at, oh, this maybe makes sense, right? It's a lot of, the visualization, try to understand, right? And what is going on, right? I mean, that's really interpolating, extrapolating, or representing the data, right? So of course, there's an effort to try to understand this, right? Say, maybe for classification, maybe the deep learning is trying to, from the information theoretical point of view, this is a framework quite popular at the time, saying maybe, if I wanted to learn a classifier using from my image X to predict its class label Y, maybe the deep network is trying to extract a feature that contains most information of X that are related to this task, this label Y, and throw away other things, irrelevant stuff, right? So maximize the mutual information between the feature Z and Y, and minimize the mutual information, subtracting mutual information between Z and X, right? It's sort of information bottleneck framework. So basically said that maybe network is trying to extract the most relevant information that can predict the label. Right? Hence, you try to maximize this mutual information, minimize those things. So when we look at this, right, this looks at this conceptually makes sense, but computationally, operationally, make no sense. Why? This is the problem we realized way before deeper networks, right? When we work on real high-dimensional data, such as images, right? This kind of framework, this theoretical framework, maybe they provide conceptual guidance, but they are actually not operational, actionable. Just like these days, right? Ilya Sukhetsov try to say, oh, large language models try to minimize the Kolmogorov complexity, right? No. Yes, you can talk about that complexity, but it's not computable. Okay? So you can talk about the mutual informations, right? They're not computable for high-dimensional structures, data distributions. They're NP hard compute, okay? Everything, almost everything you heard in the classical machine learning setting, quantities, concept, maximum likelihood, entropy of KL divergence, Jensen-Shannon divergence, right? Mutual information. None of them are computable for high-dimensional distributions, for generic high-dimensional distributions. Yes, you can do MCMC. Yes, you can do sampling. Yes, you can do all the beautiful things, but the theoretically, computationally, they're intractable. Okay, you can approximate, you can heuristic. That's what Hinton has been doing since early 1990s. Helmholtz machine, Boltzmann machine are precisely trying to approximate those things. Okay, he acknowledged those in his paper. Read them carefully. Okay, but why everybody keep talking about something you cannot compute? You can only hack. You can only heuristically approximate. You can write 10,000 papers. Each paper can argue my approximation is better than yours. Why? It works better on those instances. You can keep doing that for the next 1,500 years. There is zero progress on understanding these problems. All right, so we actually realized this problem a long time ago before, right? And let alone, especially if you're dealing with distributions in high-dimensional space, if the distribution has zero support, they have no dimensional structure. Many of those concepts, maximum likelihood, KL divergence, they're not even defined mathematically. No, why the heck everybody talking about it? Right? This was early 2000. I realized that why everybody, Renee and Shankar, we're just baffled by this. Okay? Right? So how, if we have data, even in subspace, with some noise and also those structures, right? I mean, how do you do this? Right? How do you make things computable? Right? So even for let alone very complicated manifold, very complicated distribution, even just very simple manifold, very simple distributions, subspace or mixture of subspaces, mixture of Gaussians, we don't even know how to deal with them, right? Yet everybody these days, we want to generate AI. We're dealing with arbitrary distributions, arbitrary data, right? So theoretically, we're very much behind. So just give you a couple examples. Right, this is a tutorial, so I'll go slowly, just try to get you the right concept, right? So you can see, for example, clustering. This is the standard classical pattern recognition problems, right? We do clustering. What do you learn in textbooks? Oh, we model this as a mixture of distributions, right? With some proportion pi. Each cluster has a component distribution. We write this down. We do EM algorithm. By the way, early 1990s, that's exactly Hinton works on EM algorithms. Okay, read the history very carefully. Well, everybody say this is a standard thing. We do EM algorithm. We do this. We minimize the theta pi. We alternating. There's a gazillion ways to alternating them. You learn this. We keep teaching this. But however, if your data you are clustering is in high dimension, they have low dimension structures, right? This is not even well defined. Maximum likelihood is not well defined. This is your post problem. People can keep working on them for 30 years, publishing hundreds of papers without any regret, right? No. In practice, nobody used them. Nobody used maximum likelihood to do clustering, right? But why we keep teaching students things we don't use, right? So that is the time we maybe another idea is, again, ask the same question. I realize we're asking the same question at the time 10 years ago, right? Why the heck you wanted to cluster? What do you gain from it? Apple, orange together, perfectly fine with me. Why the heck you want to separate them? What do you gain from that separation? Right? You need a measure for the gain, right? So hence we actually resort to this kind of information theory. So how do we represent the information? We actually can measure the gain before and after clustering, right? So very simple ideas, right? So if this is apple, this is orange, right? So if we don't separate them, because of the distribution in a larger space, if I want to put them together in a single bag, actually you need a bigger bag. That's the cost. The apple, orange will span together a bigger space. Now, if each of them is a smaller cluster, if I can separate them, I only need a smaller bag for each of them. I need 2 smaller bags. Even each bag costs me 5 extra cents. It's worth it because each bag becomes smaller. I gain from the volume, right? You need a measure of gain to really precisely describe why you want to do something, what you gain from it. So hence the number of bits, of course, to memory, I just use the apple orange as object, right? But for images, for digital data, you needed the bits as a measure. How many bits I store the data, right? If I don't separate them, how many bits I need to do? Or so think of number of bits is kind of the volume to measure the volume of the data, right? This is also the early idea of Shannon to quantize the entropy, quantize information in the data, right? Using bits. This is called information gain. Now the question is, remaining, if we set out to use bits, how many bits to encode, to store the data as a measure of goodness, then the question is, how the heck do I measure? Right? If you give me a bag of apple, how do I measure the volume? If you give a set of data, how do I measure that volume? Right? Again, the entropy, as I said, you cannot measure arbitrary measures. Arbitrary distributions. It's impossible to do. Packing spheres, right? So how do you measure volume? Irregular volume. What is the universal way to measure irregular volumes? This is also inspiration for information theory, guys, students. For example, my bag. What's the volume inside? It's very irregular, right? It's not a square. There's no formula for it. Right? How do you measure a space, the volume of space, or the space occupied by data? There's a very simple universal ideas, right? You pour beans into it, 1 dough, right? Pour some beans in it, then you pour it out to count, right? Then you can compare the volume, right? So you pack spheres. Of course, if you wanted the measurement to be more accurate, you use smaller sphere, right? Smaller balls. Bean counting. That's a universal way. That's actually is exactly behind the idea of coding, decoding. How do you encode your data, right? You pack all the space of the data could occupy, right? With epsilon sphere. So that's, of course, you lose some accuracy, right? Because of sphere. Then each data point, if it falls into any of the spheres, you remember its number, that's all. Right? You lose some precision of the location, but you know which ball it occurs to. That's called coding. You can convert any continuous vector into a finite binary bits. Right? That's the basic essence of information theory. Now, the question is, how do you measure the volume? Now, what is that number of spheres in certain distributions, certain data in space? Right? As I said, you cannot compute it. Most of the distribution you don't know, because that's called the rate distortion. What is the number of bits you can code your data, right? Per sample is called a rate, right? Coding rate. So first, but at least for some distribution, we're very lucky, right? For example, if the data you can approximate a Gaussian data, there is a closed form formula actually compute. If your data sample from Gaussian distribution and a certain number of samples, then this formula, this closed form formula, give you that volume, give you the number of bits. Okay? Don't underestimate this. Actually, later on you'll see almost everything we know about deep networks come from this formula. So now, once you can measure the volume of your data, how many bits, right? The coding length or coding rate of your data, then I can decide. I can weight them, right? If I separate them, how much bits I pay. If I don't separate them, how much bits I pay, right? So if I put them together, it's more than if I separate them, even with some overhead to buy the bags, right? To pay extra bags, right? I prefer to separate them, okay? Because this actually saves bits, right? If not, I stay the same. So then how do you split? That's a problem, right? So see, this gives us a measure, but you have to give us partition. I can tell if the partition is good or bad, but it doesn't tell me how to find the optimal partition. That's a hard problem. Okay, we still don't have the global solution for that. But at that time, at least we have a good measure. We can use the measure to try, right? So we use a very greedy algorithm. So we decide to start with every data points as a separate. We only merge them if we save bits. We don't merge them if we don't save bits. Very, very simple, right? Greedy algorithm. Turns out that this is still the best clustering algorithm in the world, right? You can try. Even with a lot of noise or outliers, but still, it also has this beautiful phase transition behavior, right? So the epsilon is large enough. At some point, right, every point, if you choose a very precision encoding, if the ball is very small, every point starts its own, right? At some point, it actually becomes one cluster or three clusters. It's like ice turned to water. Water becomes a steam. Kind of very beautiful behaviors, right? And turns out, this is a paper we published just before a little bit before the deep networks, right? This actually gives the state of art unsupervised image segmentation. Now, let's say you heard about all this segmentation everything, right? This is the segmentation everything, right? It's unsupervised. In fact, at that time, the performance of this is the first one, right? Even, see, this algorithm use absolutely no heuristic. It just measures the number of bits of the data. Just do simple compression. Turns out it's the best compared to all the at that time, the existing algorithms, segmentation algorithms, using all kinds of human heuristics. Loss function with all kinds of heuristics. Similarity between pixels, all kinds of edgy or context, texture, all the things, color. They use all kinds of heuristics to do similarity. No, this algorithm has zero heuristics. It just compress the image. Measure the number of bits. If you segment properly, you should save bits. Already beat all this segmentation algorithm of time based on heuristics. So the next thing is about, this is about clustering. Another classification problem is classification, right? Everybody know this is more supervised. The clustering is unsupervised, right? And the classification is supervised. If I have some labels, I want to train a classifier to tell me if it's a new data, it should belong to which class, right? I label them. This is class 1, class 2. If there's a new label, new data come in, I try to decide which cluster it belongs to, which class it belongs to. This is classical classification setting. Again, what do you learn in Statistics 101? What do we teach? Pattern recognition, statistics, right? Machine learning. Oh, let's write this as this way, right? Maximum likelihood, let's do maximum likelihood. Nobody does this, okay? Nobody does this in practice. Not a single working algorithm do this classification, okay? Not since late 1990s. They use supportive expression, right? You heard. After that, it's deep networks. Why because this is not even well defined. Why? This is why we have to change our education. Why we keep teaching students the thing we never ever use in practice with idealistic assumptions that never occur in practice. It's a very mind-boggling question, okay? But we keep teaching them. Everybody in this room, I believe, you learn classification by learning this. Okay? So again, the last thing is the same thing, right? We try to say, can we just do compare? Maybe again, ask yourself, why the heck do you want to classify? Why this point classified to this cluster is better than other ones? What is your measure of betterness? If you don't have that precisely, clearly, everything is just heuristics. And yet the probability you cannot compute. You don't have enough data, you don't have the generic distribution to make those probability well-defined. You don't have the distribution. And you only have two samples. They're yield-defined, and yet you can only use heuristics, right? So again, just extended turns out, again, you can use the coding length to measure. Right? You code them together with each class. Which class you pay minimum extra bits to incorporate a new sample. Then you classify to it. You have a precise measure of what you actually gain by assigning the data points to each of the class. So this has a parsimony flavor to it, right? Entity should not be multiplied. You minimize the coding length, right? In fact, if you read Hinton's paper about autoregression, right, Helmholtz machine, it's precisely using minimum description length as a heuristic to train Helmholtz machines, okay, to do autoencoding, right? There's nothing new under the sun, okay? And turns out this kind of classifier already has behaviors at the time. This is a NIPS paper, 2009 paper, right? So compared to Kerr-Near's paper, right? Kerr-Near's paper use this classification boundary, but does not extrapolate, right? So you can see this kind of coding, actually extrapolate to region, you never even see data. You learn the structure, right? You never get that from supported vector region in the Kerr-Near's paper. This kind of, indeed, you see this classifier learns the structure of the data and respect it and extrapolate it. But why we never use this later on? Well, it stopped, right? Everybody become busy with deep networks, right? Also, this one, it's kind of, this is done parametric. It's using data to explain data, right? It's compression. Computing bits are expensive, okay? Although in principle it works. So now, how does this connect to the modern day story? Once with this background, you will very easily understand what we're going to do, right? So these things get a little bit complicated. See, we understand subspace, we understand Gaussian. So now this day is a little bit, the data is a little bit complicated, right? A little bit higher dimensional, but it's the same principle, right? So we have data maybe not linear anymore, not piecewise Gaussian anymore, maybe there are multiple manifolds. They're low dimensional. Hence, ask yourself, right? What do we mean by represent the data? What do you want to do with it? Rather than train a network end-to-end and then call whatever you learned as a representation, right? No, you don't do that. You tell me what you want to do with the data. First, we want to identify the distribution of the data. Second, that distribution is not easy to memorize. If it's on a curve, very hard to memorize it, right? As engineers, if you have a nonlinear system, what do? We linearize it, right? The linear one is much easier to remember, much easier to use in the future. Of course, the process, you have to remember this process of linearization. You have to remember this map, F, to something standard linearized. Hence, we wanted to learn distribution that sits in a very high dimension space. What is the most effective to learn that distribution? Where that distribution is? There's only one idea. Everything you saw in the past, diffusion model, transformer, rate reduction, minimum coding length, and also different networks. There's only one idea to learn a low dimensional structure in high dimensional spaces. Compression. If you learn that structure correctly, you compress from the whole space, collapse into that structure. That's exactly what the diffusion model is doing. Collapse from a random image to the distribution of natural images, okay? And second, as I said, I don't want to just have access to that distribution, right? I want to represent it in a way I can manipulate. I want to predict the data. in the future. I want to use it, memorize, right? Hence, I wanted to linearize it if something is nonlinear. If something is non-Gaussian, I make it Gaussian, right? Since linearization. Third, right? I don't want just to learn those subspace and linearize them, right? If there's two set subspaces, well, I better make them orthogonal to each other, independent to each other, right? Well, I want an apple, not just I want to separate apple and orange. I want to really, I want to make it represented by different neurons. I saw apple, only some neurons fires. If I saw orange, some other neurons fires. The notion of sparsity, you have to think, right? So finally, self-concept has a different story, right? So the question is how, those are the minimum you want, right? So this is my list of wish list, right? I want my data to be compressed. Through compression, I learn the distribution. Second, I want to linearize them. Third, I want a different class separate. That's it, as simple as that. Turns out those ideas are very basic and powerful. That's pretty much everything there is to learning. Okay, those are the wish list, but how do you quantify them? That's the second thing, right? So this is my want, but how do you measure this goodness in terms of your wish list? Here comes the information theory, right? So just, with a little bit of history, yes, we can measure the gain of information. Why the heck do you do this, right? Each of this is what I want. Why do you want it? How do you measure the goodness, right? So for at least we know using coding length is a good measure. Although for most distribution, we don't know how to compute. But for special important class, subspace or Gaussian, turns out there's something very universal. We actually proven about 15 years ago that, right? Turns out it doesn't matter if your data if your structure is algebraic. Let's say the outlier low-dimensional subspace, or you can specify your data in the probabilistic sense. Let's say the sample from some degenerate Gaussian, right? Turns out for both algebraic subspace or probabilistic Gaussian distribution, the coding length is the same formula. It's kind of interesting, right? You can define your data in a purely algebraic structure by laying on some low-dimensional subspace, or you can define your data drawn from some Gaussian distribution. They're actually the same formula, the same upper bound, very tight upper bound for asymptotically tight upper bound for the coding length. Hence, you have a very good precise measure, at least for this class of structures. Of course, your data is not Gaussian, it's not linear. Hence, what do? You can only measure accurately the coding length bits for Gaussian subspace. What do you do then? You make them linear. Hence, the representation is that if my data has a very general distribution, subspace manifold or nonlinear, I learn a mapping to make them linear or Gaussian. Then I can measure the goodness of my feature using the formula, closed form formula. Very tractable, very efficient to compute, right? Again, what if my data, say this is for if my data lies on one subspace, one Gaussian, right? I can compute. What if, but the world consists of apple and oranges, right? At least there are two classes, right? And then I have to cluster, segment, because I gain. If I can cluster segment them properly, I gain information, right? I can compress them better. I don't have to remember the world random as a whole blue spheres. If I can pin down where the apple is, where the orange is, I only have to memorize those green balls. I save bits. I gain information, right? Save bits, save coding length, gain information is exactly the same or equivalent, okay? Now, I want to find the proper partition so that I can measure, I can actually gain. Hence, the measure, if I have k classes, of course, I can measure each class as Gaussian, right? I can compute the coding length. And I compare with what is the whole, right? Therefore, I can model all the data in the world as a big Gaussian, right? I can compute this, that's the formula that gave me the volume, the number of bits I need to encode all the data as a whole random world. Okay, if I can find the structure in the data, there are k classes, or ImageNet has 1,000. Human adults remember about 30,000 class of objects. Well, fine. If I can partition the data into proper classes, the measurement will be much smaller, right? Hence, the difference between the whole and those sum of those parts is a measure how much information I gain by learn those parts correctly. Okay, it's an objective measure. Nobody gets to say anything. The only thing you need to specify is the size of epsilon ball, how accurate you want your memory to be. Okay, that's probably the only thing you get to. You use 对吧？网球还是豌豆 to measure the volume. Okay, that's the only thing you get to choose. Hence, this object function, I want to maximize this, right? Why? I want to maximize the whole to the parts. You can see by maximize, why do you want to maximize this? This is a picture to see if you don't care about math, right? See, naturally, even there's apple and orange, only two class, it's example, right? If I'm representing apple and orange using the F figure, you feel better, right? Why? Because they're orthogonal, geometrically orthogonal, statistically incoherent, independent. That's what we want, right? We want apple and orange, never confuse apple with orange, right? But this one, yeah, they're separate. Even the number of the green balls are same, but this may get some confusion, right? They might get too close. I want to separate it. This is a less discriminative. This is discriminative, right? Hence, you want different class to contrast, to expand. You want the same class to contract. Hence, you can see this measure naturally has contrastive learning, contractive learning in together, right? Very interesting, right? Benjo proposed the contractive learning, right? Yanakung proposed advocated the contrastive learning, right? They're just a different aspect of what you want to, right? You want to compress what's similar, expand what's dissimilar. Very simple. That's probably what we're doing, right? They probably do not even deserve a name once you think about it, right? They're just very simple things, right? So as you can see, now we have the tool, at least for Gaussian distributions, right? We know the model, the log of these green spheres. That's give me how many bits. I code all the blue plus green, right? And the green is the number of rate of the two subspaces. Then the difference is we call the rate reduction. The difference, right? How much we reduce the concoding rate from the whole to the parts, right? Hence the name, rate reduction. Or information gain, other way around. Right? So I don't want to, for the interest of time, I will not get into the details. So this has a lot of similarity to contrastive learning, contractive learning, and so on. Right? Hence, we set this very, very clear. Right? We wanted to learn representation, so let's maximize the rate reduction or information gain, the measure of information gain. Right? Now, of course, you can say, we want to maximize the difference of whole minus parts, right? Now you see, okay, if we want our objective is to maximize the difference of the whole minus parts, right? Or equivalent to the number of blue spheres in between, right? Then you can say, oh, how about I just magnify the right-hand side by twice or 3 times? Then the whole minus parts will be smaller, will be bigger, right? Then what would you do? You will cry foul, right? This is unfair. Why? Because the radius is not the same, right? I can consider it much bigger. I make the ellipsoid 5 times bigger. Of course, the difference will be larger. How to be fair? You normalize the radius, right? Hence, the layer norm. How do you compare two representation? Which one gave you better measure in terms of rate reduction? You make the data first that has the same size, right? Then compare the differences. As simple as that. That's why you need to know layer norm. So hence all the norms, right? There's a batch norm, layer norm, instance norm, group norm. People still talking about them. At that time was a huge deal, right? Turns out they're all just doing the same stupid thing. Just when you do want to compare two representation, you better be fair. Just normalize your scale, okay? None of them matters, right? Hundreds of papers written about each of those layers. Anyone still care about them? Oh. I think as a community, we're better than that, okay? So now this is also, does this really do the job? I mean, this is our NIPS 2020 paper, right? Yes. This seems to be a very simple measure, right? Very, objective measure, no heuristic in that. But turns out if you're able to optimize this, rate reduction, then indeed the feature you learn will precisely meet the wish list we started with. Different classes will be a subspace of Gaussian, or a different class will be orthogonal to each other under very banal conditions, right? So you can use this to train features, right? So the good thing about this, everything starts to even the object function, right? It's not just fitting the stupid label, right? The only thing you can say if the classifier is good or not, you test on test data, okay? But here, even on the training data, you can see the coding length for the whole is expanding. For the parts are decreasing, hence the difference is increasing. You actually see what the algorithm, each iteration does to the layer, right? And again, you can see this is using, everything here is the same. You train on CPAL 10, right? 10 classes, the features. This is you train with cross entropy. Yes, it still does a very good job to give you a high accuracy classifier, but the features for different classes are not orthogonal, not independent, okay? There's a lot of crosstalks between them. But what you learn with MCR, here everything is the same. The same architecture, same training data, same optimization, okay? The only thing you change is the cross entropy, the object function, you train your network. Replace cross entropy with the rate reduction. You get a very different representations. And not only that, since each, right? See, as you know, maybe the last two lecture we'll talk about this phenomena. If you train cross entropy, you get the neural collapse, right? But here you don't. Each class is a subspace. You fit a Gaussian subspace to it, and they are orthogonal to each other, right? And since it's a subspace, I can compute its directions. I can compute the PCA, right? Each direction. You can see you align each direction. Even the image gets aligned, right? The statistic correlated, right? This is not in the label. This is actually learn the statistic distribution of the data, right? And it actually turns out that this is also more robust to cross entropy, right? Because we're feeding the subspace with many samples belongs to that subspace. Even some are mislabeled, for example. It doesn't affect too much. I estimate the location of that subspace. Hence, those subspace learning is actually rather, say, robust, right? You can have like even up to 50% of correct labels. You still get a 80% correct classifier. The subspace estimation is still relatively good, right? Now, so the question is, last 10 minutes, I'll try to wrap up in 10 minutes. So does this, again, but here we only talk about the neural network using the objective, right? The network we use is still the residual network, still the black box network. We're still using a popular network to representing the F, okay? We only change the training objective function from the rate reduction to from the cross entropy to rate reduction, right? Now, see, hence, this only verify the object function is good. Is maybe sensible. But what about network? Why we still have to use, does the ReduNet can really representing this map correctly? We don't know, right? It's a faith. They have a leap of faith that does. And why in the world want to be deep? Right? See, guys, if you are a God, right? You don't need deep learning, right? Give me the data, I give you the best partition, right? You're done. Because we have this objective function, I can evaluate. As long as whatever Z maximize that darn thing, I'm done, right? I don't need deep learning. What is the role of deep networks? Why it has to be deeper the better, right? And what are those operators, right? Linear, nonlinear operators, it's still not clear, right? People try different architectures. And also for image processing, I mean, everybody uses ReduNet or convolution neural networks, right? So I'm a computer vision guy or image processing person. Yeah, we learn convolutions. But nobody explained why in deep networks you use multi-channel convolutions. No explanation. Right? We do each channel, right? RGB each channel, we do a flat the convolution with the image patches, but we never do the chunk, right? Multi-channel. Why? Why in the world? There's no explanation of all the things. So now the question is, can we put some? I'll do very quickly. Turns out all the answers is already in your objective function, right? You want to maximize it. You want to learn a mapping from X to Z so that Z maximizes quantity, right? So you have a clear object function. You want to optimize this object function. Then how do we optimize? Right? So if that's one thing we learned from deep networks, from deep learning in the past 10 years, that if you see some, this looks very complicated, right? Some nonlinear function, log determinant, right? So we don't know how it's, definitely we don't understand global minima, local minima, saddle points, and so on and so forth, right? So I think we're bold, right? The machine learning told us, be bold. If you say something nonlinear, right, just do gradient descent, right? Say where you end up with, right? So at least that's something we can do. We can just compute the gradient and push the features around, see where you end up with, right? But as long as you do that, something interesting happen, right? So you compute the gradient, the first term, second term. This is a college calculus. Everybody in this room, if you're a college student, you should be able to do this, right? This is just computing the gradient of the object function, right? So as soon as you do that, you sort it out, it looks like this. Some matrix, big matrix inverse, apply to your data. Some big matrix, this mess, right? But they're similar, right? They're all log determinant, derivative are log determinant, right? So if you sort them out, representing this matrix with some E or this as a C, you actually see the gradient has this form. This is associated with the expansion term, right? This is associated with each class, try to compress, right? As actually the day we derived this, that night I was like, if you know statistics, right? If you have background in statistics, you recognize exactly what this operator is. Right? This operator is exactly the operator to compute the residual using ridge regression. What is that ridge regression? It's very simple. See, you have a new data points. You use all the other data points as a regressor, do a linear regression, and you compute the residual. Remember the name, residual, okay? There is another residual coming up, right? So you even know this operator is computing the residual of your data to explain other data. See, animals don't know Gaussian distribution. Animals don't even know anything, okay? But they probably know is using things they have seen before to interpreting what they have seen. Of course, if there's some difference, maybe they remember that difference. This is exactly what it does. Using data to regress themselves and computing how much residual. That's what the data residual is doing. Hence, you can see this is a schematic grid, right? So we have data on two curves, right? We want to linearize them. We also want to make them orthogonal. But globally, I don't know how to do it. But at least I can compute the gradient, the flow, right? Then we'll push data, push the data to in certain directions. That's what this does, right? Hence, then we can write down, everybody, if we engineer in this room, right? One thing we're taught, if I have some algorithm, your teacher asks you to draw the diagram of data flow, right? So from the previous iteration to the next iteration, if you draw it, right? It goes through each channel, C kicks class, and some expansion, and there is a gradient descent, Z plus that gradient, right? So what does this look like to you? Residual network, right? In fact, even better. To represent it is similar to what is the next generation of the residual called the ResNext, right? Which has better performance, right? People realize put more parallel channels into each block, each iteration, get a better performance, right? This is from Hao-Kai-Ming or Xie Sanling's work, right? And there's a difference, right? Difference in the residual network, they initialize those blocks, they have to train, they don't know what the operators are. They train end to end. Here, every layer, we know exactly what the operators are doing. We do forward computing. It's forward constructed. Those parameters already predetermined. And this actually also looks like these days Google is training mixed job experts, right? Yeah, this is a long time ago, 2017. This guy actually came to Berkeley, give a talk, right? And you know that recently, right, there was a paper last year, Hinton wrote about 404 algorithm. First time, he admit, nature doesn't do backpropagation, okay? The network should be forward constructed. And the forward network is precisely optimize the goodness of features. But he doesn't specify what is goodness. Here you have the answer. And does this work? Yes, you can actually do this. One thing I want to say, just one last thing. This is just compressing data, right? So if you force your data, where the convolution come from? Right? This is still compressing data, right? This still just a matrix, right? There's still a matrix operating that. So what is the structure? Why this C and E should be convolution? Convolution arises when you try to compress translation or rotational in sense instance together, right? See, for this object, right? It's the same object if wherever I put it, right? So hence it's the same object. Therefore, you want to compress them together, right? So rotated or translated instance, you want to compress them together into the same subspace. If you do that, this compression algorithm, this compressor, remember this operator, right? E operated, remember computing this residual, computing the self-regression residual. That operator, that gradient automatically become a multi-channel convolution. It exactly has the form of a multi-channel convolution. No ambiguity about it. Right? So the multi-channel convolution actually could rise naturally because it's an operator for compression, compressing equivalent objects, images. Right? And there's a lot of, so yeah, hence this is a huge matrix. Turns out that the matrix has a lot of structure, especially if you want to enforce invariants, translation invariants or rotation invariants. The operator becomes convolution network naturally. Right? Very interesting, right? Our brain, we all know our brain don't compute in space or temporal domain, right? What are our brain computing? Frequency domain, right? Brainwaves, spikes network. Neurons fire by frequency, send information about the frequency of the fire, not the amplitude, okay? And this is the first mathematical evidence to say there's actually the computing in the space domain, the cost is n proportion, n is the resolution, how many pixels your image. If you're computing the space domain with this operator, it's n cubic. But if you're computing this in the frequency domain, it's linear in the number of resolution. This is the only piece of evidence I know, right? Can explain there's advantage to computing in the frequency domain. And maybe nature found it, right? And for the first time, right, you actually can write down, just optimize the object function, maximize information gain or minimize the coding rate, right? It's the each layer is just compress it, reduce the coding rate, right? You can write the entire deep networks, every single parameter, what they do, linear, nonlinear operators, what they do, right? Right, so turns out, right, this is all the thing we know about deep networks, right? What is convolution doing? What is normalization doing? What is each linear operators doing? Why we do this residual? Why do skip connection? They're just, everybody just looking at the small pieces, right? And everybody thinks, that's everything, right? And many people become very arrogant, right? I say, it's the one time, deep network is all you need. Reward is all you need. Attention is all you need, right? Are you serious? How shallow you can be, right? You can make that kind of statement, right? Right. So for all the students, I keep saying every time, every tutorial, your next paper title should be something is not enough, and you will become very famous, right? Because everything has a paper say, attention is all you need, something, they're gonna be, historically it will be a joke, okay? Right? So there's a lot of things we don't understand, right? There's way too many things we haven't discovered, and we need to be more humble and more curious. So, you can, also, there's one problem though, don't get me fooled, right? This framework, this ReduNet network, we can construct a network this way, but it's very expensive, okay? Computing this E matrix is a huge matrix, all the training data, high dimensional data, large batches. You have to compute the matrix and you do the inverse, okay? Hence, at the time, we can only test on a small data set, in a small number of classes, small number of lower resolution images, and so on, right? But they work, right? Including invariance. They can achieve really invariance on every single rotation translation, rather than just using augmentation. Here you can build a network that's truly invariant, right? So this is using augmentation. Here you can see that if you build a network, invariant Redu network, you actually get 100% almost high 90s invariance for rotation translations, right? But there are problems with this. As I said, this doesn't scale, right? Because it requires, even you computing in frequency domain, still, right, with high dimensional spaces, those EC operators are extremely expensive to do, right? Hence, and there are early attempts still try to design neural networks. And then ReduNet is one of the early attempts. There's also scattering network using wavelets to build those operators to achieve invariance and to build the deep networks. Again, it's very expensive. Can build 2 or 3 layers and explode. Number of filters explode. Although the Redu network, the number of filters stays constant, but each one is very expensive to compute. If the resolution is high, those matrices are very hard to invert, right? So that's actually leads us to the recent work that Sam will talk about, how to make this scalable, right? So I'll conclude a little bit with the last few minutes, right? So the principle of parsimony, you can see clustering. Why do you call it cluster? What do you gain? Well, minimize coding length. You want to classify. Why? How do you measure the gain from classification? And how do you learn representation? Why do we want them to be linearized? Why do we want them separate? Again, it's information gain. Minimize the coding length, the relative coding length for the whole and parts, right? And yes, coding length is very expensive to compute, but for Gaussians, piecewise Gaussian, mixed Gaussians, subspace, yes, there are formulas for it. All right? Hence, you can do finding global minima still very, very hard, but I can do greedy descent. And that incremental operator, right? To based on gradient, precisely resemble the operator of deep networks. Next time you'll see in Sam's work, right? That's also what the transformer does. And at least for the first time, the neural network was incepted exactly about 80 years ago, right? In the past 80 years, the practice deep network has always followed the guidelines on the left. Fit some input, output, randomly initialized, back propagation to train. After training, still a black box, right? You test it as a black box. The feature you call them hidden and latent, which is ridiculous, right? You spend billions of dollars train a model, you call it what you have learned is hidden. Okay. And now from the information theory point of view, if you really clarify the objective of your learning, is try to gain information, then the object function is white box. The architecture to iteratively optimize the object function naturally give you the architecture, it becomes a white box mathematically. And even the feature you learned will be precisely structured. Subspace piecewise Gaussian, that's all. Right. So there's many open questions, I don't go. Now, just to allude to the next talk, right? See, we know rate reduction, we try to reduce the rate, right? Or minimize the coding rate, or maximize information gain. We want to compute in doing this, right? Even do this incrementally. But this star thing is very difficult to compute, right? Very big to do a big matrix inverse. You can do it for small data sets. But we're engineers, right? If something difficult to compute, what do? We approximate, right? This is just, look at this, right? In a scalar case, this is 1 over 1 plus x, right? Calculus, guys, how to approximate 1 over 1 plus x? Taylor expansion, right? Do a Taylor expansion of this term. What do you get? Just take the first root. What does it look like, right? It looks like exactly like a tension head. See, I just want to put a few words, right? I hope it's useful for you as a student, right? There was a time when things start with black box, right? People don't know why res network or the network works better or worse, right? Or the transformer works. So there was a time around 2015 or 17 or 18, there's still probably something still going. People believe, well, there's maybe better networks out there, right? So they do random set search called AutoML, right? Very popular, hundreds, thousand papers published. People burn a lot of GPUs to look for better architecture. In the end, still these days, 2 survived, right? ReduNet, transformers, right? There are Turns out they're both are trying to residual attention. They're trying to approximate the gradient of the coordinates. Right, just different names, different slightly approximation to the same quantity. And once you realize the network architecture is doing optimization, there's gazillions of ideas we haven't tried. Everything you see today, the Redu network, the next Crate network, are the most basic, naive idea of doing optimization, okay? We haven't invested, there's tons of 300 years of advanced ideas to do optimization better, to design better optimization operator. Even gradient descent, how many braids there are, right? They have not even been tried, right? Just be humble, right? All we have done so far is very, very primitive, very, very naive, actually, very brute force, actually, right? We're not nearly at the end of the humanity. Okay, as I think people suggest, AI is going to take over, right? It's going to, wipe us out. No, we're not. So anyway, there's also a lot of many other things I want to just say, right? So this also combined to generative model. Today I talk about the one direction, X to Z, and I think Sam will talk about how do we go back, right? We have the mapping from X to Z, the encoding. Turns out the decoding, right, should be inverse, right? Somewhat inverse. And what is mathematical operator then? Are they the same or different kind, right? Curious, right? So this is sort of the related to this talk, right? There's a serious talk I've touched upon, right? From clustering, classification, and representation. And this ReduNet is kind of conceptual framework. It's not practical yet, but the next talk will be make it practical, okay? And so that's why the recent work is about white box transformers. There's some, if you want to like to, the ReduNet is still a very principled concept, right? Clarify a lot of understanding, right? There's a GitHub, some additional topic resources you can play with, Google Colab and the Jupyter Notebook. And if you want something more broadly understanding some of the mathematical background, right? Some of the talks in this conference, you just also have a textbook about all the high dimensional data, understanding the distributions and so on. There's also a course I teach at Berkeley, and also here now I'm at Hong Kong U, right? So anyway, so this is just try to summarize. If you forgot, if you don't understand anything, remember this sentence. Deep bracket convolution neural networks architecture are just iterative optimization scheme for compression, okay? To try to optimize information gain, to try to compress data, right? Nature, right? Our brain, when we're born, we're not preloaded with PyTorch, okay? If we want to optimize something, we have to wait to realize something physically. Our neural networks are precisely realizing those optimization algorithms, layer by layer. Each layer does things a little bit better, okay? That's the interpretation, and I think that, and the next talk, I think will probably, Sam, is Sam here? Ah, here. Sorry, I will take a little bit more time, but I won't take any questions, but maybe after the tutorial, we'll do some more discussions. Yeah, if there's time. Okay, thanks.